Okay, so last part of notes is basically just kind of an extra review, and we're going to talk about this, and then we're just going to do 3 AP problems, okay? And that's what we're going to do today for that extra kind of review. So, and the last one, I will warn you, is the hardest, so really hang in there, okay? First 2, we're going to build your confidence, and that last one, we're just going to bring it all down. No, it's a good one to see because it's a challenge, okay? You gotta challenge yourself. You can't just have all these. Okay, so we're gonna just look at the 2 error bounds. We have the 2 that are the Lagrange and the alternating series. And what are these guys telling me? Josiah. In general, just in general speak, what are both of these guys telling me? General speak, layman terms. Yeah. Which that next term is your what? No. In general, I heard it. Error. Okay. So he just said exactly what I wanted to hear. He said, hey, the actual term, or not the term, but the actual value minus the approximate value, that error is less than the next term. And is this the next term? Is that the next term? Yeah. Okay, so they're basically stating the same exact thing. The only little tricky part is when I don't have that whole alternating series, I have this. That's the tricky part of finding that max output value, basically. Okay? That's the only little hiccup. Okay. So the only other thing I want to make sure we remember is we are really thinking of that guy with absolute values as well. Okay, even if that term ends up being negative, we're going to take the absolute value of it. Okay, so that's the only little thing I wanted to discuss. So are these guys so incredibly similar? Absolutely. The next term in the alternating series would just be that guy. Okay, and that's what I really wanted you to see. Okay, so we are going to do, like I said, 3 problems. All of them at some point or another are going to have the alternating series error bound or the Lagrange error bound. Okay. You say you love Lagrange? Oh, love Lagrange. Yes. Okay. My work here is done. Okay, so part A, and I gotta say this is from an AP test. If you had this problem, you would be singing hallelujah, because I think you could go get all of these points without a lot of difficulty. Let's just discuss, and then I'll let you go and we'll check, okay? Part A says determine the interval of convergence. So the first thing you're going to look at is you're going to say in your head, is this geometric? Is this a geometric? No. Okay, you don't have the A times R to the N. So it's not geometric, so the only other thing you're going to use is the ratio test. And in the ratio test, we have to do what? Check endpoints. If it was geometric, would I have to? No. Okay, so we can all do that one. This next part, thank you, is the f double prime of 2. When I want to go find those values, f double prime of 2, f prime of 2, f triple prime of 2, do you remember what game we played? The what game? And it was at the very, very, very end of 8-7. Let's see if I can find it. those guys? The matching game. Okay, so we find the matching game. We take like the general and we set it equal to whatever's going on. Oops, gosh, I think I just. Oh, I'm all over. I can't go back. Alright, hold. Okay, so we take that general and we set it equal to what our term is. Sorry. So we match. We play the matching game. Right? Okay, so that's not too bad. Guess I. So that one, again, it's a 2. And then on this one, they're actually telling you to use what? Alternating series error bound. Okay. Not a lot of thought there. They're telling you what to do. Yes? Okay. I'm going to give you 10 minutes. I want you to try to do this problem. I'll pause the recording.
Diverges.
Okay, we're going to check A, and then I'll give you a little bit more time, actually, okay? Let's just check A first. So I didn't write out the whole limit, because I'm just going over this with you. But your limit, as you did the n plus 1 term over the nth term, should have yielded x minus 2 over 3. This guy converges by the ratio test. Did you include that somewhere? Or tell me you're doing the ratio test.
Yeah.
That's fine, as long as you are stating that. So that's going to converge when this happens. Okay? So then I get it into my form of that x minus the c is, x minus the c is less than the radius of convergence. My radius of convergence in this case was 3. And then I drop my absolute value bars, and I have to check my inputs. When I plug in the 5, I reduced it to here. When I plugged in the -1, I reduced it to here. And the big thing on that guy is remembering that this is the same as that. Yes? And that's the, usually the tough part when you're going to reduce. So I got these guys to reduce. This guy diverged by the p-series. And this guy, you showed your 2 steps with the limit and decreasing, and you say it converged by the alternating series test, right? So my final answer was -1 less than or equal to x less than 5. That was worth about 5 of the 9 points on the AP test. Pretty big. How did you do? Did you fix anything? Do pretty good? Okay. I'm going to pause again and finish B and C. Let's see how we did on the last 2. So on part B, we have to use our general equation that says f double prime of 2 over 2 factorial is what's in front of that whole x minus c squared, right? So we're 27. I don't care if you leave it 3 squared times 3. Okay? So now we get to go solve for that. So f double prime of 2 equals 2 factorial over 27. And again, 2 factorial is 2, so if you just write 2 over 27, that's fine as well. Good? Okay, I have a really quick question on this. Is 2 a relative max, a relative min, or neither? Remember what we did on that part? We first had to see what prime of 2. Is f prime of 2 equal to 0? No. So is it a relative max or min? Neither. Okay, because I get a value out. Okay, so back to our problem. Part C now says use the first 3 non-zero terms of the power series for f to approximate f of 1. So f of 1 is approximately 1 plus 1 minus 2 over 3 times 2 plus 1 minus 2 squared over 3 squared times 3. And there's my answer. Done. Don't have to reduce. Okay? Silly of you to reduce. If you decided to reduce, this is what you have to have had. Okay, if your answer doesn't match that, then now you just missed points for doing it wrong. And you just wasted some time. Okay, so then it says, show that the actual f of 1 minus that approximation that we just had is less than 1 over 100. So my actual minus my approximation, well, I know that the error is less than the next term. So my next term going on up here is this guy. But when I plug in the 1, negative 1 cubed is a negative. But I'm going to make it still positive. So I know I'm going to have a 1 over that 3 cubed times 4, right? And then what's the only little thing you have to say? Hey, that guy is less than 1 over 100. Yeah. Okay, guys. Okay, this is the question. So, is this a true statement? I mean, think about that. 27 times 4, that's bigger than, what, 25 times 4, right? So this is a smaller number. Do we have to simplify any of these things? Is this okay? Do you understand conceptually what you're saying here? Yes? Okay. So there is the first of the 3 we're going to do. Okay. Now we're going to go to this one. We're increasing a little bit of difficulty as we move forward. Okay? Oh, just one. That's so weird. Okay. Thank you. Emily, read this.
Let h be a function having derivatives of all orders for x greater than 0. Select values of h and its first 4 derivatives are indicated in the table above. The function h and its 4 derivatives are increasing on the interval 1 is less than or equal to x, and x is less than or equal to 3.
Okay, so the first thing of interest to me is that these are all for x greater than 0. I have the first 4 derivatives, and then this is interesting. I'm not quite sure why they want to say it, but I'm sure that there's a reason why they said it. Yes? So that's just my, okay, got it. Continue.
the first degree Taylor polynomial for h about x equals 2 and use it to approximate h of 1.9.
Pause. Let's do that. So it's about x equals 2. What's that tell me? The center. Okay, so my center is 2. And it wants me to go out how many degrees? The first degree. 1. Which is basically just the what again? Linear approximation, or the what line? Tangent line. Okay, you do that. I hope so. Go. Part A, sentence 1. I'm going to give you 30 more seconds for this sentence. This first sentence. It should all be good. Alright, so first sentence in A. The Taylor polynomial of degree 1, and we're centered at 2. So again, I'm going to look here. We are centered at 2. So I'm only worried about this guy. Agreed? Okay, so that would be 80 plus 128 times x minus 2. Everybody good with that? Anybody not good with that?
So when it asks for the first degree Taylor polynomial, do we have to label it the t someone of x? Or could it be y?
You could have y. They're not, as long as you have this part, they're not really going to care what you label it. I just always do this so I know that was my first degree. Okay? Because later I'm going to do the third degree. So what are you going to label it? Are you going to label it y as well? Because now you have 2 y's. So this is a better way of keeping track. And then it says use it to approximate h of 1.9. So h of 1.9 is approximately 80 plus 128 times 1.9 minus 2. Am I going to reduce them? No. I'm done. 2 points in the back. Okay. So then, this is the next sentence is when we have to think a little bit harder. That first part was just very routine. Got it. Is this approximation greater than or less than h of 1.9 and explain your reasoning? Whew. Okay. What piece of information would I have to know? Don't say it, if what is increasing? Okay, well, here h of x is increasing. So that's not the right piece of information, but you're kind of getting there. You're almost there. Okay, if h double prime of x is positive, or if what is increasing, h prime of x. So if I know I am concave up when h prime of x is increasing, or when h double prime of x is positive, right? And then if I'm concave down, then h prime of x is decreasing, and h double prime of, is negative. So when I'm concave down, all of those linear approximations, those tangent lines, will all be what? Over or under? Okay, so all of these will be over when I'm concave down. When I'm concave up, all of those linear approximations are going to be under approximations, right? Of the actual. So I need to look for something of that information. Where did they tell me this? Well, the last sentence here. The function h and these four derivatives, so the derivatives are what? Increasing on this interval that we're talking about, right? So this is telling me that h prime is increasing, so therefore h is concave up. So if h is concave up, then this is a under approximation or underestimate. Okay, go fill yours in. You have to justify, so see if you can write what is needed. Okay, so are we all good with that? So my question for you, on part A, how many of you did this part? Y minus y1 equals m times x minus x1. How many of you did that on part A? Find it. Okay, how many of you guys said, oh, my general guy is f of c plus f prime of c times x minus c, and I stopped there. How many did that on part A? Okay, those were your two options. So if you didn't raise your hand, I don't know what you did. Okay. Okay, so on part B, now it says write the third degree Taylor polynomial. So I can't go to my default of my tangent on B. I'm going to have to know my whole long formula for B. Okay? Go try B. That's my hint to you. Buckets. I sold if you try to reduce this. I forget to help you. Okay. Agreed? That would just be ridiculous. So this part's the same. But now I gotta continue. I remember I was a grader for this problem. And I was so mad when they did this right here. These exponents. It was horrible to go. Do you know how many people messed those up? They did 488 and then 448. So many students wrote the wrong thing because they were like so similar and they, I don't know, it was like, are you kidding me? You couldn't have just made it 1/3 or something. But you know what? It's the same concept. Why would you make it this horrible expression? Anyway, so there's the first part. Questions on that? That's just using that general thing. And then the second part is plugging in the 1.9. See how you better not reduce this? I mean, I understand if you want to put like -0.1 or something, but even then, just right? Isn't that kind of gross? Like, I was like, that's kind of mean. You all of those horrible numbers. You could have just put nice, pretty numbers and did the same concept. It's not like the horrible numbers made a difference. Anyway, that was my opinion on this problem. Okay, good on that? Okay, really, really quick, just a little extra, because we're going to make sure we go. Tell me what oh no, it's on there, just kidding. Okay, never mind. Go to part C. That's the Lagrange error bound. I can tell you, use the Lagrange error bound. No. So you can do this. You can say, no, you don't ever, you can say that h of 1.9 minus the t sub 3 of 1.9, okay? Right. Yes. Okay. So you could write it like that. You could, even if you wanted to, you could say, hey, that equals y, and then you could have put y here, for all I care. Okay? So I would not write all of that in there again. Good question.
Almost all of it.
Yeah. So if it was me, this I wouldn't have done that. I would have said that my t sub 3 of 1.9. Okay. Yes.
Okay, so for your approximation, would you put it, if you put it h 1.9 approximately, or could you be like
T sub 3 of 1.9 equals that. Yes. Hey, Tori, this was what power that we stopped at. So this next one is going to be what the fourth. So it's the fourth derivative, but the weird thing here is I say the d, right? And then I'm going to say what? So remember, this is our x value that we're plugging in here. And this guy goes x minus c, right? So what is our x? X is 1.9. That's the same x. Our center, though, is the 2. So that's the x minus the c. And I have it to the fourth over the fourth factorial. So now, as I have this fourth derivative, I'm looking at the 2. They told me that all these guys are, like, the derivatives are increasing and all that fun stuff. And so they basically told me that that's going to be my upper. Okay? This right here, the fourth derivative of the 2. So I could put that value in for my fourth derivative of z. Okay? It's never going to be a real overthinking process. So that's what I can put in down here. So, that's what I'm saying. The max output between 2 and 1.9. So since all the derivatives are increasing, the max output would be at the 2. Because we're looking between our center and our x value. Okay. So this is that 584 over 9 times the 1.9 minus 2 to the 4th over 4 factorial. And then all I have to say is that, hey, that guy is less than 3 times 10 to the negative 4. Do I have to reduce it? No, but if you reduced it, is it going to be a true statement? Yes. Okay. We have the last one now that we're going to do together. What? Yes. You do not have to reduce anything here. As long as you don't have like an h of x or an x or something you didn't plug in a value for. But it's all numerical and all operations, then you're fine. Okay? Okay, last one. Let f and g be these two functions. Okay. The graph of, what's that saying? F. Fifth derivative of f is given between negative 1/2 and 1/2. Okay, thank you. So that's what they're telling us. Right. Let me ask you guys this. As soon as you see this, and this is like back from AB, we're thinking back to calculus. Okay, so back to AB, as soon as you see that, what is popping into your brain? Huh? There should be something popping into your brain. You know, like the little thought process, like thought. Okay.
Yeah.
How do you do it? How do you make it? My thought bubble. Okay. Okay. What thought bubble pops into your head right here? Okay, the second fundamental theorem of calculus. Okay, so when I see that, why is the second fundamental theorem of calculus popping into my head? Because there's an x on a bound. So when I see a variable on a bound of an integral, I'm thinking second fundamental theorem of calculus. So I'm thinking that's probably probably going to be applied somewhere, right? This is the fifth derivative going on here. I'm probably thinking I'm going to need that at some point. And besides that, I really don't have any other information or thoughts just by reading this. But that's what jumps into my head first. Okay, so now let's actually go down and look. Write the first four non-zero terms of the general term for the Taylor series for e to the x about x equals 0, and you have 30 seconds to go.
Oh,
Okay. Okay, everybody go with that? Zach? Then it goes into the trickiness. They said write the first four non-zero terms of the general term for f. Where was f? Right here. What are my steps for manipulation on this one? Plug in what for x? X cubed. Then multiply through by x. So if this is me, I would take 2 steps to get to my answer so I don't mess up. That's what I would do. So first, I'm going to just ignore that part and do the e to the x cubed. Then, after I find that, I'm going to multiply through by x. If you can do it all in one swoop, great power to you. I'm going to do it in 2. Please don't look at what I write until you've tried it. Bless you. Everybody good here? Did anybody write x to the 3 plus 1?
Yeah.
That's fine too, that's wonderful. Okay, same thing. Okay, yes.
You also like simplify the exponents, or do you just leave it
You leave it how?
like x cubed squared?
You could, but it's probably going to be more challenging later. Okay? So as far as simplification on that, I would. Okay? Okay, any more on part A? Okay, part B. Write the first. So part B says write the first 4 non-zero terms of the Taylor series for G. So now we're on. See, now we're on part B. Well, G was the integral from 0 to x of f of t. So what is f of t basically here? This is f, right? So this would be what? T plus to the 7th over 2 plus t to the 10th over 6 plus dot, however far you want to go, dt. Yes? So they want me to find the first 4 non-zero terms of g. What am I going to do next? Integrate. And evaluate from 0 to x. We're given term by term. That's why I'm integrating term by term. I could have wrote this as a series and actually done this just as easily if you really wanted to. Like we could have came over here and said this is x to the 3n plus 1 over n factorial, right? And then my antiderivative, how we did all that with series, and then did my terms. You could have done that. I'm going to go ahead and just do it term by term. Plug in 0, all the terms go to 0. And this you're going to notice, this value down here is always going to be where you're centered, so that when you plug them in, it goes to 0. So if I was centered at 1, like if I had t minus 1 in all of those, you're going to see that that would be a 1, so that all those terms would go to 0. So my answer for the first 4 would be that.
Would you have to show that you plugged in 0
No, if you went and saw this, and you went to that, you're fine. Okay? They would put a 2 there. They're never going to give you a number that doesn't basically zero out. Yeah. Yeah. Otherwise, that would just suck. Okay?
So what
They won't do that to you.
do like 2 to x or something and then do like x minus 2.
Yes. Yeah, if they had x minus 2, they wouldn't put a 0 there. Because that term wouldn't zero out when we subtract. Yeah. Okay? Okay. So there's B. Told you this was a fun one, right? Okay, so now we're going to go to C. So, sorry, any more questions on B? I really want to put this one together because it's challenging. C. Let P sub 5 be the 5th degree Taylor polynomial. Oh, sorry, no, C, just kidding. Find the value of G, the 5th derivative of 0. G of x plus this. Oh, guess what's going to come into play, guys? Finally, yeah, because how many, I'm going to have to take the first derivative, which I'm applying my, okay, so what does this become? That's f of x times 1, right? Minus f of 0 times the derivative of 0, which is 0. So all of that is just f of x. Keep going until you get to the what derivative? Until you get to the what derivative does C tell you to go to? Fifth. Okay, so keep going until you get to the 5th. And some of you may just put dot 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 G to the 5th equals. identify? Huh? Oh, you know what? I am doing it a longer way. Hold on. Okay, this is good practice for us. I just thought I want to use it. Okay, hold on. We're going to do the same thing with the matching, but let's do this really quick, okay? So what did you get your fifth derivative to be? The fourth, right? And then I can go and match. So I could say the fourth derivative of x over 4 factorial equals, I go match it to the f here, which would be what? 1. I don't know why I did it this way. Just thinking through. Okay. So the fourth derivative of x, which is the fifth derivative, right, of x is going to be, or sorry, not of x, of, what are we saying, 0. Thank you. 0. Is equal to 4 factorial. Okay, silly me. We already had g, though. Right? So we could have matched right there. Okay. So I could have said g to the fifth of 0 over 5 factorial equals, go match here, and what do I have? 1/5. Oh, guess what that's going to be? 4 factorial. So g to that fifth of 0 equals 5 factorial over 5, which is 4 factorial. So, oopsie. That's fun practice. Okay. So either way, here were 2 different ways to get the answer. There you go. Okay? Shannon, is that what you were saying? Okay. So then, last step, and what we did will actually help us for part D. It says, let p to the fifth be the fifth degree Taylor polynomial for g. And they want us to use the Lagrange error theorem here to show that p to the fifth of 1/2 minus g of 1/2. Oh, they switched the order. Does it matter? No, because there's absolute values. Okay, so whatever. So in ours, it's going to be less than or equal to the what? G to the 6th derivative of z times the x, which is 1/2 minus our center of 0 to the 6 all over 6 factorial. So I'm good with everything here. I am like WTF on this one. Where can I go figure that out? Oh, hold on. But the graph, I want g to the 6, and the graph, okay. The graph was f to the 5th. Oh, but g to the 6th equals f to the 5th. Okay, so see how that part C actually kind of helps helps me anyway. We are going to have to do it eventually. And I'm looking between where I am centered and what I am approximating. What is my max output here? What did you say? 500. So 500 is the max here. And there is my upper error bound. I told you that was a hard one. I know. That's why I wanted to do it together.